Hi everyone, this is our lecture on section 1.7, which is on integrals using the inverse trigonometric functions. Before we get into that, let's briefly review what those inverse trigonometric functions are. So recall the function y equals tangent x. Sorry, just trying to fix that. So y equals tangent x. Now, an inverse function doesn't always exist. An inverse function for a function exists when the function passes the horizontal line test. All functions must pass the vertical line test, that is, every vertical line must intersect the graph in at most one point. So here we intersect in 1 point, here we intersect at 0 points, because it's an asymptote. For an inverse function to exist, you actually have to pass the horizontal line test as well. Okay, so we restrict tangent x to the domain minus pi over 2, strictly less than x, strictly less than pi over 2. And then you reflect this graph around the line y equals x to get the inverse function, the graph of the inverse function. And that's it right there. And that inverse function is called arctangent of x. Now, the book uses the notation tan inverse x rather than arctangent x. They mean the same thing. I like this notation better because tan inverse x often can be confused as following. Don't mistake tan inverse x, the whole thing, to the negative 1 power. And what happens when you take something to the negative 1 power? It means the reciprocal of it, right? But that's cotangent of x. But that's different than tangent inverse of x, which is arctangent x. So I don't like this notation because it gets confused with that. So I just use this one. For the sine function, we restrict sine x to the domain minus pi over 2 less than or equal to x, less than or equal to pi over 2. And then you get this little bit of the graph, which satisfies the horizontal line test. And so you do your reflection, and that's the graph of arc sine x or inverse sine x. Secant. So we restrict y equals secant x to 0 less than or equal to x, less than or equal to x less than pi over 2, along with pi over 2 strictly less than x less than or equal to pi. So this gives us the full range of the secant function from 1 to plus infinity, and then from minus infinity to negative 1. And then this passes the horizontal line test, and the inverse function looks like this. So the domain here is from negative infinity to negative 1, and then from positive 1 to positive plus infinity. Right, that's our reflection around the line y equals x. Excuse me. All right, let's remember the derivatives of these functions. And when you're looking at the derivatives, you only need to look at arc sine, arctangent, and arcsecant. You don't need to look at the cofunctions because they're very similar in terms of what the derivative is. They're just negatives of the derivatives of these. Anyway, the derivative of arcsine of x is a function that looks totally different than that. 1 over 1 plus x squared, or I'm sorry, I got mixed up. 1 over the square root 1 minus x squared. This one is 1 over 1 plus x squared. And this one is 1 over absolute x So the slope of the inverse secant function, the arc-secant function, the slope of this is always positive, as you'll notice, right? That's a positive slope right there, and that's a positive slope right there. It's always a positive slope, so that's why that absolute value is there. Is even for negative arguments of x, you get a positive slope. These can be combined with the chain rule. With the chain rule as an outer function. So the derivative with respect to x of arc sine g, well, that's going to be this with x replaced by g times g prime. This one, similar. This is 1 over 1 plus g of x squared. So instead of x, you have g of x. The whole thing multiplied by g prime. And then this one is, looks like this. G of x, absolute value, square root g of x minus 1. Okay, so that's the derivatives of the inverse trigonometric functions. Okay, the derivative of arc sine is not arc cosine, right? The derivative of sine is cosine, but arc sine is a totally different function. 1 minute, I'll be right back. Okay, so let's take an example. So calculate integral or antiderivative 1 over 9 plus 4x squared. Okay, so this looks a lot like the arctangent one. Of course, the derivative of arctangent is this, right? It's not 1 over 9 plus x squared or 9 plus 4x squared. So we need a 1 here rather than a 9. So what we do is we factor out the 9 on the bottom. So we do 9, and then this becomes 1 plus 4x squared over 9, or 4 ninths x squared. Right, let's bring that 1 ninth out front. All right, 4 over 9 x squared is actually the same as 2/3 x, the whole thing there, squared, right? 4 over 9 is a perfect square. It's 2/3, well, it's a rational square, as they call it. It's 2/3 squared. All right, so this is 1 plus 2/3 x, quantity squared. So this is a linear degree 1 polynomial on the inside of the derivative of arctangent. Okay, and the derivative of that linear function is just a constant, so it's not like hanging around here somewhere, but it doesn't need to be because it's just a constant. So here's the composition of functions. So this should be u, the inside of this composition. So let u equal 2/3 x. So du is 2/3 dx. So 3/2 du is dx. And here's the two substitutions that we need to make. So this is equal to 1/9, 1 over 1 plus u squared. So now that looks like the derivative of arctangent. 3/2 du. Take that 3/2, bring it out front, and I get 1/6. 1 over 1 plus u squared du. This is exactly the derivative of arctangent of u. So its antiderivative is 1/6 arctangent u. Plus c. And then u is, what was it? 2/3 x. And that's your final answer there. Okay, so a variation on the arctangent formula. Another example. So this is not, they don't have one of these in the book, but I would like to show it to you because I think it's kind of nice. So another example using arctangent. What's one thing you notice about this polynomial here? So that's the derivative of arctangent, right? What's the deal with the polynomial on the bottom, x squared plus 1? You can't do what to it? You can't factor it. We can't factor it using rational numbers. Okay? So it doesn't have rational roots, in other words. So that suggests that if you have any degree 2 polynomial that's not factorable, right? So notice that, well, let me write it this way. That x squared plus 1 and x squared plus x plus 1 both don't factor. So that suggests that this is somehow arctangent. Okay, how is it arctangent? Well, you have to, what's known as complete the square. Okay, what's the coefficient of x here? Right, so coefficient of the middle term x is 1. So now take that coefficient 1, divide it by 2, and square it. You get a quarter. Okay, take the coefficient of the x, the positive coefficient, I mean even if there's a negative there, take the positive coefficient of x, right, divide it by 2, and then square. And you get a quarter. So what do I do with that quarter? I do like this. This is x squared plus x plus 1/4 minus 1/4, which is 0, plus 1. See what I did there? So right here I added in 0. So plus a quarter minus a quarter, so those will cancel each other out, right? Just make 0 and give me x squared plus x plus 1. This is known as completing the square. It's one way to complete the square. And what that means is, well, this right here is a perfect square. It's x plus a half. It's x plus 1/2 squared. So this is equal to 1 over x plus a half squared. And then this is plus 3/4. So we can factor out the 3/4. Oops. 1 plus, so this becomes 4x plus, well, 4/3 x plus a half quantity squared dx. Pull this 3/4 out front, pull it out from underneath here, and it becomes a 4/3, right? 1 over 1 plus. So this is going to be the square root of this, which is 2/3, or 2 over root 3, x plus a half, that whole thing squared. Right, so instead of just the x plus 1, x plus a half squared, it's x plus a half times 2 over root 3 squared. 2 over root 3, when you square it, of course, is 4/3. And then when you square this, you just get x plus a half squared. So now to finish this out, let u equal this, just like we did in the last example. Let u be equal to this linear polynomial. So what is this? 2 over root 3 x plus, so that becomes 1 over root 3 if you multiply this through. So then du is 2 over root 3 dx. So root 3 over 2 du is dx. So this is equal to 4/3 antiderivative 1 over 1 plus u squared. Right? Root 3 over 2 du. Bring this out front, and this becomes, so the 4 and the 2, they cancel, 2 root 3 over 3, antiderivative 1 over 1 plus u squared du. A lot of little tricky bits in here, but I think it's a neat problem. I just wanted to show it to you. There isn't one in the text like this, and I'm not going to ask it for you. I'm not going to assign it to you on an exam, but I just wanted to do it. So this is exactly the derivative of arctangent of u. So the antiderivative is arctangent of u. Putting that back in terms of x, comes 2 over root 3, 2 times root 3 over 3, arctangent of that. 2 over root 3 x plus 1 over root 3. So kind of a, an annoyingly complicated linear function, but there it is. Okay, so the thing about arctangent is that it's the derivative of 1 over a quadratic polynomial that doesn't factor over the rationals. And as a matter of fact, if you have some polynomial that doesn't factor over the rationals, there's another condition that you have to say about that polynomial, but it's not a very restrictive one. Once you complete the square, you can turn that into the derivative of an arctangent in a standardish form. Okay, let's do an example of one with a sine. So there's several examples in the text that use this kind of trick here. So watch for antiderivatives of the form f of g of x, where g of x. So we looked at inverse trig functions on the outside of a composition. What if they're on the inside of a composition, where g of x is equal to arctangent x or arcsine x or arcsecant x. So for example, something like this. So the integral from 1/2 to 1 of arcsine x over square root 1 minus x squared. So this is equal to the integral from 1/2 to 1. So you've got this arcsine x here. And then you have the derivative of arcsine. Right, so this is exactly the kind of form that I was talking about here. You have some function in terms of arcsine, and then the derivative of arcsine multiplied by the whole thing. So in this case, what you want to do is let u equal g of x, which is either arcsine, arctangent, or arcsecant. In this case, it's arcsine. Okay, so let u equal arcsine x. So du is the derivative 1 over square root 1 minus x squared dx. Put this over here. Make your substitution. So that's the integral from x equal to half to x equals 1. Arc sine is u times this 1 over square root 1 minus x squared times square root 1 minus x squared du. And those cancel. All right, as they should with this u substitution technique. So this becomes the integral from x equals a half to x equals 1 u du. Antiderivative of that is just 1/2 u squared from x equal to half to x equals 1. So it's 1/2 arc sine x squared from 1/2 to 1. Okay? So it's 1/2 arc sine 1 squared minus arc sine 1/2 squared. Arc sine of 1 is pi over 2, right? What angle has sine of 1? That's pi over 2. And this is pi over 2 squared minus arc sine of a half. What angle has sine equal to 1/2? That's 30 degrees. By the way, the values of these inverse trigonometric functions have to be in radians, not in degrees. Okay, the output of the arc sine function is in radians, not in degrees. When you're doing any algebra, so I mean, or arithmetic, we're doing some arithmetic with these functions. So you have to output a non-labeled quantity. When you say the arc sine of 1 is 90 degrees, you mean 90 degrees. 90 degrees is a labeled quantity. It's not just a number by itself. Right? Right? It's like saying 90 degrees Fahrenheit or 90 degrees Celsius. Right? They mean two different things, and they're labeled quantities. We want something that's just a number. So when I say pi over 2, when I say radians, okay, that's not a label. It's just referring to an angle in its native form, its native numerical form. 2 pi is a full rotation of a circle, because 2 pi times the radius is the full circumference of the circle. So 2 pi is an angle of 360 degrees, full rotation of a circle, but it's a numerical quantity. It's not right, because 2 pi times the radius equals circumference. Right, so it measures the length of the circle. It's just a purely numerical geometric thing. We just say radians just so we know what we're talking about. It's not a labeled quantity. Anyway, sorry for all that long-winded explanation there, but what do we have here? We got 1/2 pi squared over 4 minus pi squared over 36. So that's equal to, what do we got there? So 36. 4 times 9, right? So that's 9 pi squared minus 1 pi squared, so it's 8 pi squared over 36 over 72, so that's pi squared over 9. And there's your final answer. Okay. Let's take one more example. How about this one here? How long is this video? Maybe we'll just do it during discussion. Yeah. No, let's do it. I'll do it quickly. So let's do, how about the integral from 0 to 3 . I guess we can't do to 3 because that would be an improper thing. It's not continuous there. So let's do 0 to 1. Okay? So integral from 0 to 1. 0 to 3 halves. 0 to 3 halves. 0 to 3 halves, 1 over square root 9 minus x squared. So again, it looks like arc sine. Okay? And what we need to do is factor out the 9 here. So that's 9, 1 minus x squared over 3. Okay? Factor the 1/9 out of here. Because it's underneath the square root, when you factor it out, you have to take the square root. So that becomes 1/3, integral from 0 to 3 halves. 1 over square root, or I'm sorry, that's a 9, not a 3. Square root 1 minus, so x squared over 9 is x over 3 squared dx. Let u equal x over 3. So 3 du is dx. So this becomes 1/3 integral from x equals 0 to x equals 3 halves. 1 over square root 1 minus u squared, 3 du. The 3 and the 1/3 cancel. So we're left with the integral from x equals 0 to x equals 3 halves. 1 over square root 1 minus u squared du, whose antiderivative is arc sine u, and evaluate that from x equals 0 to x equals 3 halves. Okay, so it's arc sine x over 3 from x equals 0 to x equals 3 halves. So that's arc sine of a half minus arc sine 0. Arc sine of a half is 30 degrees minus arc sine of 0, which is 0. So it's pi over 6. Okay? So that's all for the lecture on 1.7.